Good morning, students. We will start back where we had last time stopped. I'm just going to recap first what exactly are the different oxidation state. This table was there for the last lecture. I'm just again recapping back. If you see, we're going to talk mainly about the 3D series. 3D series, that's mainly from scandium to zinc over there. Now on this table, just something important. I want everybody to observe this. When I'm talking about the ones which are highlighted, the highlighted ones are its stable oxidation state. Like for example, scandium, you will see scandium more stable with respect to what I can call as scandium stability is more in its +4 oxidation state. Vanadium is more stable in its +5 state. Chromium stability is more in its +3 and its +6 oxidation state. Manganese is in +2 and its +7. Iron is basically, we all know, ferrous and ferric, that's +2 and +3. Cobalt is in +2 and +3 again, that's cobaltous and cobaltic. Lower is us, higher is ic. Nickel shows more stability in +2. Copper has more stability in +2, that's cupric, and zinc has only one state, that's +2. So what's the highlighted ones are its stable oxidation states, which is nothing but subject to its different. One is stability is explained on 3 factors. Listen carefully. One, it is with respect to the availability of what we can call as the unpaired electrons. Because if you remember, I told you what is normal oxidation state? Electrons of its valence shell. So for 3D, electrons of the 4s is the minimum oxidation state. And what's the variable oxidation state? Variable oxidation state corresponds to electrons of 4s plus unpaired electrons of 3D, that is n-1d. So with respect to that, we can say okay, there is one what we have as nothing but the stability rule. Half filled, completely filled and empty orbitals are more stable than incompletely filled orbitals. Second, in some cases those states are not there, like chromium in +3. It is neither half filled nor completely filled, still it is more stable. That's because of its hydration enthalpy. Is this clear? That's one. Second, in some cases it's also over there along with hydration enthalpy. What we can call over there is nothing but its lattice energy also, as well as in some cases it also will depend upon ionization energy. Okay, let's start now. So this is the oxidation states. Now we'll go to the next part and see. First we're going to talk about, last time we spoke about the atomic size. I'll recap. Atomic size decreases from scandium to chromium, and from chromium to zinc it remains almost the same. That's because of the poor shielding of the d electrons. Second we spoke was the IE value, where IE value, as we say, across a period from left to right it increases, but the increase is marginal, where the third IE is always highest, then the second, then the first, where there are some exceptions in between where it achieves half filled or completely filled orbitals. Now we're going to talk about the next factor over here, that's gonna about its standard electrode potential. If anybody remembers, people redox reaction, we have spoken about electrode potentials, right? What's electrode potential? That's the capacity or the tendency of the electrode to either get oxidized, or the metal to get oxidized, or its ions to get reduced. The series we have is the SRP series, standard reduction potential values, where all the elements are arranged in the form of electrodes in their decreasing order of their SRP values. Where if you remember, all the non-metals which readily undergo reduction, that is the process of gain of electrons, there is a decrease in its oxidation state. They are all placed at the top of the SRP series, where hydrogen is where fluorine is at the top of the SRP series. In between we have hydrogen over there, and then below hydrogen we have all electropositive metals which are good reducing agents. All right, so the order is above hydrogen all oxidizing agents, they readily undergo reduction with positive values of SRP. All below hydrogen are with negative values of SRP, mainly the electropositive metals, that's the S block elements, and some of the D block also, where we say that these metals are the ones which undergo oxidation, so the SRP is negative, where at the bottom we have lithium. So fluorine on the top, lithium at the bottom. Fluorine, strongest oxidizing agent, lithium, strongest reducing agent. Now in this electrode potential value, all these are electropositive metal, so their SRP values are negative. except one in the 3D series, and that is copper. Copper is the only one which has a positive SRP value. The reason being, cupric ions have more tendency, is this clear, to undergo reduction rather than copper metal getting oxidized. In few exceptional conditions only copper gets oxidized. Otherwise cupric ions always get reduced to copper metal. So cupric ions and copper, they are placed above hydrogen. So copper has a positive SRP where all metals have negative SRP. Have a look at it, what I'm discussing here. Just see on the slide, please. It says the observed value, where it says the unique behavior of copper having positive value accounts for its inability to liberate hydrogen from acids. People, what is the logic of inability? Inability liberating hydrogen matlab copper has to get oxidized, the H plus ions have to get reduced. So copper has less tendency, but there is an exception where we say with respect to concentrated nitric acid, it does react, but there are exception part, otherwise majority cupric ions will always get reduced to copper. And what is the reason there? It says the high energy of transformation is not balanced by its hydration enthalpy. There are two reasons for the same. One is its hydration enthalpy as well as its lattice energy. So two factors contribute that the ions have more tendency to get reduced rather than the metal getting oxidized. Then apart from this part, what it says, the E0 values of manganese, nickel and zinc are more negative than expected from the trend. If you see the graph over here, just see this part carefully. Mn value, is this clear? Then comes nickel, as you rightly see, this is the value, see the graph, that's the value of Mn what we have. Then we have the value of nickel, and then we have the value of zinc over there. That's the standard SRP part. They say it's little different. Why like that? We'll come to that. Before that, two questions to discuss. Listen carefully. It says Cr2 plus is a good reducing agent and Mn3 plus is a good oxidizing agent, even though both have D4 configuration. Let's understand this. Chromium, atomic number 24, argon 4s1 3d5. So if it is Cr2 plus, one electron first always from the valence shell. So one from the 4s, one from the 3d. So it will be 3d4. Mn, atomic number 25. That's argon 4s2 3d5. Mn3 plus. So is this clear over there? So two of the 4s, one of the 3d. So both have D4 configuration. Now what is the logic? It says chromium 2 plus is a reducing agent. Reducing agent, substance that undergoes oxidation. So Cr2 plus becomes Cr3 plus. So what's going to happen, people? There will be a loss of electrons. So D4 will become D3. Alright, which is neither, again, nothing to do with the stability rule part. Whereas in the other part, Mn, which is a good oxidizing agent, what happens? Oxidizing agent undergoes reduction. So Mn3 plus reduces to Mn2 plus. So it gains an electron, D4 becomes D5 over there. Now what is the logic? Still D5, though anyway we know it's stable, but still Mn is an oxidizing agent and chromium is a reducing agent. Just see this explanation. I'll just explain you. Little bit it goes in the depth of coordination compounds. That's chapter which is going to come ahead with respect to the complexes what I discuss. See here. It says Cr2 plus, both have, it changes from D4 to D3. It says the latter has half filled T2G orbitals. It says T2G, that's in unit 9, that's coordination compound. Now what's T2G? Listen this carefully. D orbitals, as we all know, the D subshell, is this clear if you observe, has got 5 d orbitals: dx square minus y square, dz square, dxy, dyz, dxz. Now when light falls or the ligands are coming, then what happens? The orbitals split into their lower energy and high energy level. Is this clear? This is basically what we call as a splitting theory. We'll be doing in coordination. Okay, when a ligand comes in, then the orbitals split into lower and high energy level, where one energy level is called T2G, that's a name given, and one energy level is called EG level. So T2G is basically the 3 orbitals, alright, depending on an octahedral or a tetrahedral complex. If it's an octahedral complex, T2G is made up of dxy, dyz, dxz, and the EG level is dx square minus y square and dz square. So if there are 3 orbitals in the T2G, and people, if the D3 is there, as per Hans rule, all will first go in their parallel spins. So that's why 1 1 1 will go. So D3 is stable. Everybody clear? So what I'm trying to talk, it's Hund's rule, but along with what we have as a splitting theory. Okay, when the ligand is coming to donate the lone pair, the d orbitals, d subshell has got 5 orbitals. They split into 2 levels, T2G and EG. Depending on the complex, whether it's octahedral or tetrahedral, these orbitals will get divided. So for octahedral, T2G is dxy, dyz, dxz, and the EG level is dx square minus y square and z square. So if D4 as chromium is a good reducing agent, so what's going to happen? D4 becomes D3. So D3 means in the xy, yz, xz, 1 electron will go. So that will be half filled with respect to T2G. That's why chromium stability is more, with where +2 gets oxidized to +3. And for Mn3 plus, that will get reduced to Mn2 plus, because there it becomes D5. So that's the 2 reasons. And one more question there down. The E0, matlab the standard electrode potential values of copper is positive, that's plus 0.34. What is the possible reason? Now the reason they have given here, one is enthalpy of, actually it's a correction, it's given delta HA. It's not delta HA, it's with respect to its lattice energy. It should be L and low delta H hydration. Matlab the reason is simple. Cupric ions readily undergo reduction because of 2 reasons. One, because of its low hydration enthalpy, and second, because of its nothing but high lattice energy. So these 2 reasons contribute to what we call as cupric ions, is this clear, which will readily undergo reduction to give copper, hence the SRP is positive. Next people, now this is basically what we have, a table giving an idea to you, that is the stability wise how it goes. The first one is its enthalpy over there with respect to its atomization, forming its atoms, because metal, whenever it gets oxidized or reduced, first we have atomization, that it forms its free atoms. Then it's delta H1, that's the first ionization, then the second ionization, then hydration. So we have a combination of 3 things with respect to electrode potential. One is atomization or sublimation, we can call solid to gas, if the metals are generally solid. So atomization is forming its free gaseous atoms. That's one. Second, it's ionization enthalpy, and third is its hydration enthalpy. Combined effect of all the 3, is this clear, will prove over here that whether it will undergo oxidation or reduction, and in some cases like copper, it's also contributed with respect to lattice energy. Now here all values, no values to remember, only copper as a positive value, rest all are negative, meaning all are placed below hydrogen. Now see what it says, stability of Mn2 plus, now Mn again I told you 25, 4s2 3d5, Mn2 plus, so over there nothing but Mn2 plus 4s2 goes, so d5, so half filled, more stable. And same way zinc plus, Zn2 plus, zinc atomic number 30, argon 4s2 3d10, first electrons out, please keep in mind valence shell, so 4s, 2 of the 4s goes, 3d10, all d10 completely filled, so it's stable. Whereas look at that, E0 of nickel is related to its high negative enthalpy of hydration, meaning nickel Ni2 plus, nickel is 28, remember the mnemonic, no? Science teachers very cruel, mentally fatigued, causing nightmares. 8, 28. Argon, nickel will be argon, 4s2 3d8. So if it's Ni2 plus, 4s2 goes, 3d8, neither half filled nor completely filled, still more stable. Why? Because of its high enthalpy of hydration. So three effects together, and in some exceptions it is one more effect which contributes to electrode potential. So one, it's atomization or sublimation for the metal from the solid to its gaseous state where it forms free atoms. Second is its ionization. Third is its hydration. Together combined gives us the standard electrode potential, and in some cases it also its lattice energy, like copper. Then next we have people, now the trends in M3 plus to 2 plus, matlab +3 oxidation state changing to +2 oxidation state. Like say for example scandium in 3 plus will have a noble gas core. Scandium is atomic number 21, argon 4s2 3d1. So Sc3 plus, 2 of the 4s, 1 of the 3d. It will have a configuration of argon, so more stable. Same way Zn2 plus, what I discussed, see on the slide there, that has a stable D10 configuration. And Mn in Mn2 plus will have a D5 configuration. Same way ferrous and ferric, more stable will be ferric. Why? Ferric loses Fe, Science teachers very cruel, mentally fatigued. 6, 26. Fe will be 26, argon 4s2 3d6. So for Fe2 plus 2 of the 4s, so it's 3d6. Fe3 plus 2 of the 4s, 1 of the 3d, so it's 3d5. So ferric will have a d5 configuration, which is more stable. And same way, again a part which will be explained more clearly in coordination. Low value of vanadium. Please mark this important and note this from the MCQ point. Low value of vanadium is attributed to the stability of V2 plus, and that's again because of half filled T2G level. Again, let's understand. Scandium, titanium, vanadium 23, argon 4s2 3d3. So it says V2 plus, so 2 of the 4s out, so 3d3. But when the orbital split, when the ligand comes to form complexes, it splits into 2 levels. For octahedral complex, T2G is of low energy level, so 3 orbitals, dxy, dyz, dxz. 1 electron will go because V2 plus will have 3 unpaired electrons, so again half filled. That's why we say stability is more. Next, now comes people over here, trends in the stability of higher oxidation state. Now generally one simple rule, or you can call it as a thumb rule to keep in mind with respect to oxidation state. Lower oxidation states, elements are good reducing agent, like ferrous and ferric. Ferrous is a good reducing agent. It will increase the state from +2 to +3. Whereas ferric is a good oxidizing agent. It will get reduced back to ferrous. That's how we talk. So lower oxidation state, elements are good reducing agent. Higher oxidation state, they are good oxidizing agents. They undergo reduction. I repeat, elements in the lower oxidation state are good reducing agents. They undergo oxidation. Elements in the higher oxidation states, they undergo reduction. They are good oxidizing agents. Now see here, it says highest state is with respect to, look at that, VF5, CrF6, +7. In 3D, the maximum is Mn, that's +7 state over there, what we have. That's one. And people, the highest states are generally with fluorine. Is this clear? Or it's with oxygen. Why? Fluorine shows only one oxidation state. We all know it's a super halogen. One state of -1 only, smallest atomic size, no vacant d orbital. Is this clear? Highest electronegativity in the entire periodic table, and in the SRP series placed on the top. That's why fluorine shows only one state, -1. That's why maximum states can be formed with F, because Cl, Br and I, keep in mind, they have vacant orbital. So apart from negative, they also show positive oxidation states also. That's one. So it says the ability of fluorine is due to the high lattice energy. That's what we have as cobaltic fluoride. Just see the slide. Or it says the high bond enthalpy in terms of covalent compounds. And similarly, vanadium, what is raised to here, what is raised is the oxidation state. Vanadium in +5 is only represented by VF5, where vanadium loses 5 electrons because F has only -1 state. Alright. Now these are the states, people, of what these compound forms. So in +6, chromium forms CrF6. That's what you have to see. Is this clear? That's one part. Then next, people, more examples to discuss over here. Alright. Like for example, look at that. Oh, there's a mistake. This arrow, technically what you see should have come down. Over here the arrow should have been there. Okay. Now what it says. Now lower state and higher states to understand. I'm just reading this part. Have a look at the slide. What it says here. On the other hand, all copper 2 halides are known except the iodide. Like cupric oxidizes iodide, meaning cupric ions will get reduced to copper and iodine will get oxidized to iodide. If you're getting confused, make it simple. Write the oxidation state. Just see on the slide, please. Cupric ion state will be what? +2. Here Cu2I2 it becomes. That's cuprous iodide. Copper is in +1 state. And I hope you know why I write Cu2I2. Dimerization. Because generally it gets cancelled, right? Should be Cui. But it's Cu2I2 because cupric ions cannot exist single. Like we have spoken, mercurous chloride, Hg2Cl2. So the two mercurous ions combine to form a dimer. Same way, two cuprous ions combine to form a dimer. So Cu2I2. So cupric +2 becomes cuprous +1, and iodide, which is -1, becomes 0. That's the part. And it says copper 1 are unstable in aqueous solution because it undergoes disproportionation. I hope everybody remembers this word. simultaneous oxidation and reduction of the same species. So that's what's exactly seen. Look at this reaction. Cupric will get 1 mole, 2 moles are there. So one gets reduced, cuprous gets reduced to copper, and second, cuprous gets oxidized to cupric. That's what is the part. So its unability is there, and why plus 2 is more stable? Again same. It's low hydration enthalpy and lattice energy. The stability of Cu2 plus then Cu plus 1 is due to its much negative enthalpy of hydration than Cu plus 1, which more than compensates for the second ionization enthalpy of copper. That's one. Then it says it coincides the highest oxidation state people we have, scandium 2 plus. Yeah, all this part is fine. They've just given us a theoretical point for you to understand over here. Yeah. Now what it says, beyond group 7, look at this. No higher oxides of Fe are known, although ferrates where Fe is in plus 6 are formed. Now ferrates are basically cage type of a compounds where it forms a complex. So in complexes Fe can show plus 6 state, otherwise normally Fe is plus 2 and plus 3. But they readily decompose to Fe2O3 and O2. Besides these, oxocations stabilize. Now oxocations are what? Cations combining with oxygen. Is this clear? In their oxidation states. So you have basically an ion of oxygen, is this clear, is called an oxocation. So oxygen containing cation, that's an oxocation. Like vanadium in plus 5 as VO2 plus, vanadium in plus 4 as VO2 plus, and vanadium for titanium 4, that's in TiO2 plus, that way. So here the ability of oxygen to stabilize its states exceeds with fluorine, and the highest state of Mn with fluorine is MnF4, what it forms, whereas the highest oxide it forms is Mn2O7, that's dimanganese heptoxide, where Mn is plus 7. So stability is more with respect to oxygen as compared to fluorine. Why? The reason, oxygen can form pi multiple bonds. Is this clear? Whereas fluorine can't form a pi bond. Fluorine will always form a single covalent bond only. So that's what it says. The ability of oxygen to form multiple bonds to metal explains its superiority. So we say the maximum oxidation states are of the elements with oxygen and fluorine, where more superiority is with oxygen because of its ability to form pi bonding. That's one. Then the next we have people to talk now. Look at these oxidation state, what I was just discussing, where with Mn it shows highest, that's in Mn2O7. Have a look at the slide. Chromium over there, that's plus 6 CrO3. Is this clear what we have? Then Cr2O3, that's another stable, that's in plus 3 oxidation state what we have. That's one. And copper generally is CuO, and it also forms Cu2O, both in plus 1 and plus 2 state. That way. Okay. Now look at this question, what it says. How do you account for the increasing oxidizing power? What is increasing oxidizing power? Lower to higher, that's increasing. Of VO2 less than Cr less than MnO4. Simple. See the oxidation states, people. VO2 plus, oxygen is 2 into 2, so that's minus 2 minus 4. There's a plus charge, so vanadium is plus 3. Cr2O7 2 minus 2 into 7 minus 14, so the 2 vanadium has to be minus 2 plus 12, so plus 12, so each chromium is plus 6. And MnO4 minus 4 into 2 minus 8, outside charge is minus 1, so Mn is plus 7. So what it says, increasing oxidizing power. So what is it? Just please pen this down, important point with respect to MCQs. Higher the oxidation state on the central atom, more is the oxidizing power. Meaning, what is oxidizing power? Tendency to readily undergo reduction. So in higher oxidation state, it is a good oxidizing agent. It will readily undergo reduction. Now see here, one question, in-text question. How would you account for the irregularities variation of IE of the first and second series of the transition elements? Now people, what is the reason for the irregularities with respect to the parts? Simple, people. Stability rule. Empty D0, half filled D5, completely filled D10. These three, if this is achieved, then the IE values are much higher. That's the irregularities. Clear? So stability rule, empty, half filled and completely filled orbitals. They will be more stable. Then next people to talk over here. Alright. Now the chemical reactivity what we have. The ones placed above hydrogen, people, as I said, they will undergo reduction. They are good oxidizing agents. Ones placed below hydrogen, their metals will get oxidized. Matlab, their SRP values are negative. In other words, the one placed below in the reduction half, suppose I say reduction half Zn2 plus gains 2 electrons to form zinc. That SRP is negative, minus 0.763 volts. Zinc, so the backward reaction takes place. Zinc will readily get oxidized to zinc ions by the loss of 2 electrons. So zinc will readily get oxidized. Clear? That's the way. So this is all about the part where in the first part it's only basically it says, look at that, the metals of the first series with the exception of copper are relatively more reactive and oxidized by 1 molar H plus than the actual rate by which these metals react with oxidizing agents like H plus ions is sometimes slow. For example, it says titanium, vanadium, they are passive, then decreasing tendency to form divalent cations. This general trend towards less negative is related to the increase. So look at this part. This point is important. See on the slide, please. This general trend towards less negative E value is related to the increase in the sum of the first and the second I values. So they are moving from left to right. We see the negative value goes on becoming lesser. The reason is because of the summation of his first and second I. Then it says E0 value of Mn, nickel and zinc are more negative than that expected. Again, why they are more negative? Irregularities, same bhashan. Again, empty, half filled and completely filled. So look at that, half filled, that is one reason what we have, D5 for Mn, that's for Mn2 plus, and completely shelled for zinc, that is D10. And then it says for nickel, people mark this point important with respect to MCQ, nickel stability is more in +2, not because of stability, because of its high enthalpy of hydration. Cu plus 1 more stable, its enthalpy of hydration is more, Cu2 plus is more stable than Cu plus 1 because in +2 state, its enthalpy of hydration is more than Cu plus 1, and also the second factor is lattice energy, that one. So all above hydrogen, that's like say chromium ions, they will all displace hydrogen, means in other words, chromium ions will get oxidized and H plus ions will get reduced. Clear? That's one. Now next, people, look at that. These are very simple and easy questions. From the first row they have given, what is the reason for the irregularities? That's what we just now discussed. One is, it's a summation of three things. Either enthalpy of, what is the net electrode potential? E0 value is calculated how, people? Three variables to add. Either enthalpy of atomization or sublimation. Matlab, the metal going from the solid state to its gaseous state. So carbons, suppose I have zincs going to zinc gaseous, I can also call it as enthalpy of atomization, forming its free atoms. Second is ionization, and third is hydration. Okay, so look at that. The E0 values are not regular and can be explained on the basis of, look at this part. One is their IE values and also their sublimation enthalpies. Is this clear? That's why we have irregularities. The next one, E0 of Mn3 plus Mn2 plus couple, matlab the pair which will undergo over there +3 to +2, so it undergoes reduction, is much more positive than Cr2 plus to Cr3 plus or Fe3 plus to Fe2 plus. Matlab if I take Mn with Mn2 plus, that's placed below hydrogen. But if I take Mn3 plus with Mn2 plus, that's placed above hydrogen. What is the reason for this part? Again the same way. Large transition. The large third, look, it says the third I value is very large for Mn, which requires to change, that is from D5 to D4. That explains why +3 is of less importance. Clear? And +2 is more stable because it gets converted to D5. Then look at this part. Why is the highest oxidation of metal exhibited in its oxide or in the form of fluoride? We right now discuss, people, in the form of fluoride because it's a superhalogen, and oxide because oxygen has a tendency to form multiple pp pi bonds, but more stability is in oxygen, that's oxide. And second, which is a stronger reducing agent, Cr2 plus or Fe2 plus? Now if I have to say, what do you will say? Cr2 plus will be a better reducing agent as compared to Fe. Why, people? Same way you will have, if I say Cr2 plus, one will go from 4s, one will go from what I can call as the D5, so it will become over there 3D4. So when I talk about the 3d4, what is happening over there? All right, so here d4 will get converted to d5. Matlab Cr2 plus will get changed to Cr3 plus. So d4 will become d5, so half filled. Whereas Fe2 plus means already Fe was 26, so it was 4s2 3d6. So in Fe2 plus, it's only 3d6. So if it becomes Fe3 plus by loss of electrons, is this clear over there? There also out of the two, what is happening? D6, is this clear, is the one that will come. So here what we'll say over there, stability will be more, all right, as compared to, so Cr2 plus will be a better reducing agent as compared to Fe2 plus. That's one. Then, okay, now coming to people, the next periodic function, magnetic properties. So we have spoken about atomic size, ionization enthalpy, about the electrode potential values over there. All right, now magnetic properties. Tendency of an electron to be attracted in a weak magnetic field. We have three properties: diamagnetism, paramagnetism, and ferromagnetism. Diamagnetism, the species is what do we say, diamagnetic character. They are repelled in a weak magnetic field. That's called diamagnetic behavior. Paramagnetic behavior, they are attracted in a weak magnetic field. And ferromagnetism, they are permanently attracted in a magnetic field. Means in other words, ferromagnetism is enhanced paramagnetism. Okay, and to calculate, we have a spin only formula, that is spin with respect to the electrons. If anybody remembers, we have discussed Bohr's magneton. Nu is equal to root of n into n plus 2, where n is the number of unpaired electrons. So if I know the number of unpaired electrons, we can calculate its Bohr magneton. I'm just reading this part, just see here. First is the three definitions: diamagnetism, then is about paramagnetism, and also about ferromagnetism. Okay, and that's all because of the unpaired electrons. Now what it says, for a compound, just see this part, just see on the slide please. For the compound of the first series, that's 3D of transition, the contribution of orbital angular momentum is effectively quenched, and hence this is of no significance. Orbital angular momentum, that was with respect to what we call as the magnetic quantum number. So it says that effect is negligible. So we talk with respect to only what is called as the spin only formula, and that formula is, please say this formula everybody, nu is equal to root of n into n plus 2. N is the number of unpaired electrons. So very simple, if I am talking Ni2 plus matlab 4s2 electrons are gone, so it's 3d8. D orbital 5 are there, so 5 parallel as per Hund rule, 3 anti-parallel. So how many unpaired? 2 unpaired. So n will be 2 here. So root of 2 into 2 plus 2. So 2 plus 2, 4. 4 into 2, 8. It will be root 8 will be the answer over there with respect to nickel 2 plus ions. So n is the number of unpaired electrons. Clear everybody? Alright, that's how it goes. So based on this part, people will be talking now. Look, it says a single unpaired electron will have a magnetic moment of 1.73. How 1.73? If n is 1, that's basically root 3 then. Is this clear? So root 3 is 1.73. Then next people, this is the table now. Okay, what are the observed and the calculated values? That matlab how this formula came into picture. That's the logic there. Okay, like 1.73 we just calculated because D1 will have one unpaired electron. See the slide please. And that's why the value as per the formula, and what is observed is around this much. So it is in line with what we observe. That's how it goes. Okay, now look at that. Magnetic moment of a divalent ion, that's the word to catch, whose atomic number is 25. Now everybody, 25 is what? Mn 25, argon 4s2 3d5. Divalent matlab it loses 2 electrons, so d5. So d orbital 5, d we have 5 orbitals in the d subshell, so all 5 as per Hund's rule will be in the same spin. So 5 unpaired electrons. So formula root of n into n plus 2. So root of 5 into 5 plus 2. So 5 plus 2, 7. 7 into 5. Root 35. Root 35 approximately 5.9, because root 36 is 6. So approximately that answer. So see here. That's the part nu is equal to. That's nothing but 5.92. Clear? That's one. Clearly? Then next it says over there, calculate the spin only magnetic moment of M2 plus aqueous ions. Now what is the M2 plus, where Z is equal to 27? Now 27 is basically cobalt. When I say M2 plus, M2 plus matlab 2 electrons of 4s goes, so it's 3d7. Don't take full 7, count unpaired. First 5 parallel, 2 anti-parallel. That's how 7 goes. So number of unpaired will be 3. So if n is 3 over there, so 3 root of 3 into 3 plus 2. So 3 plus 2, 5. 5 into 3. That's 15. That's root 15. Root 15. Answer will be close to around 3 point. What I can call is around 3.8 or close to 4. So 3.87 is the correct answer. Clear everybody how to calculate? Everybody understood this, how to do it? Okay, M2 plus, I repeat once again. 27, that's cobalt. M2 plus, matlab in its plus 2 state. So 4s took a 2 electron goes, so it's 3d7. First 5 in the d orbitals will be parallel, 2 anti-parallel. So number of unpaired, 3. So root of n into n plus 2. So 3 into 3 plus 2. 3 plus 2, 5. 5 into 3, 15. Root 15. Closer to 4 because root 16 is 4. So that's around 3.87. Okay. Then the next we have, after this, formation of colored ions. Now D block elements are the ones which forms colored ions. Like for example, first question comes, what is the concept of color? Color is attributed with respect to light falling on a particular compound. And if it has unpaired electrons, then that light which falls, as I said, the crystal field splitting, what I said, it splits into 2 parts, the d orbital, what I just said, T2g and Eg. Same way people, if the orbital split up, electron jumps from a low energy level to a high energy level. So important part, for a compound to show color, there has to be presence of unpaired electrons. And if there are unpaired electrons, then when light falls in the visible region, that's 400 to 800 nanometers, in that range, a particular element in its ion state, depending on the unpaired electrons, it absorbs a particular wavelength of the white light and it jumps from a lower level to a higher level. Now when it jumps from a lower level to a higher level, whatever portions of the white light are absorbed, the remaining portions which are unabsorbed are reflected back on the compound. Like for example, if I say copper, Cu2 plus, we all know cupric ions are bluish green in color. Copper sulfate, any compound if you observe, is bluish green. What's the logic? Copper sulfate, copper is in plus 2. Plus 2 means copper was argon 4s 1 3d10. So one of the 4s, one of the 3d goes. So its cupric ions configuration is argon 3d9. So in 3d9 it will have one unpaired electron. So that one unpaired electron will jump from the low energy level to a high energy level, like T2, G2, Eg. Now it will absorb a particular wavelength of the white light. Now it absorbs over here the yellow and the red portions of the white light. So the blue and the green portions which are remaining are reflected back on the compound. So keep in mind, the color what we see on the compound is not the wavelength of the light absorbed, is the remaining wavelengths which are reflected back on the compound. Okay, so this table is important. I'm marking some of them. So it's called the complementary color. So the remaining wavelengths, unabsorbed wavelengths, are reflected back on the compound. I'm marking few of them. Just observe. Achha, so if there are unpaired electrons, those will show color. What if a compound has no unpaired electrons? So if there are no unpaired electrons, that compound will be colorless because there is no unpaired electron to jump from lower to higher. What if it is completely filled? Again the same, there are no unpaired electrons. So for empty and completely filled, the compounds will be colorless because none of the portions of the white light are absorbed. So there has to be presence of unpaired electrons for it to absorb over there and jump from lower to higher. That's one part. Now see this few of the colors to understand important ones. Titanium 3 plus, that's purple in color. Please write down and keep what I'm highlighting because these are the important ones. Vanadium 2 plus, that's violet in color. Then Cr2 plus, that's blue in color. Ferric Fe3 plus, that's yellow. Then Ni2 plus, that's basically a green color. And cupric, that's a bluish green color. These are some of the important ones what you need to know. Clear everybody with respect to the concept of color? Okay, that's one. Next comes an important feature. We're going to do this in coordination, but an idea, tendency to form complexes. Now in complexes, if you remember, we have discussed you have a central atom, you have a ligand donating its lone pair, And depending upon how many bonds are formed between the metal and the ligand, we have a term coordination number. We can predict its hybridized state, is this clear, and the shape of the molecules. All right. Now, what is the logic for this compounds to form complex? The compound's tendency to form complex is very simple. One, it should have a small size and it should have a high charge by size ratio. So higher the charge, smaller the size. So greater charge by size ratio. Availability of vacant orbitals for the ligand to donate lone pairs of electron. That's why mainly all D block elements are the ones which form complexes. I've given few idea over here or few complexes to understand. Like for example, the first one, what do you see? FeCN6. This first one, FeCN6 4 minus. That's ferrocyanide ion. Ferro. Fe is in ferrous state. That's what you see in the diagram. Just see what I'm highlighting. This is the +2 state. These are the 6 ligands, 6 cyanide donating the lone pair in the vacant orbitals of Fe. So coordination number is 6, and the hybridized state, cyanide being a strong field ligand, it is D2sp3, octahedral. Okay. Same way, look at the next one. Ferricyanide ion, FeCN6 3 minus. First was FeCN6 4 minus. And FeCN6 3 minus, just see please just see the slide. Fe is in +3 state, that's why the name ferricyanide ion. Again the 6 cyanides, so that's going to be octahedral geometry. Again the hybridized state, D2sp3. And then when you are making it, we see the number of unpaired electrons to gauge whether it's diamagnetic or whether it's paramagnetic. Then one more, cuprammonium ion, that is CuNH342+. That's basically a square planar structure, DsP2 hybridized. That's what you see here. Look at that, copper in the center, 4 ammonium ions at the 4 corners of the square plane. So that's basically what we have as nothing but a square planar geometry, DsP2 hybridized. Oxidation state of copper is +2. Clear? That's one. I've explained the whole part, what is happening. This is just for understanding. We're going to do this again in coordination. Copper atomic number 29. That's basically over here. So first part 4s1 3d10, that's what you rightly see. Second part, it loses 2 electrons, so it's going to be over here Cu2 plus may the configuration is 3d over here as you observed. Look at that part. One unpaired electron jumps, is this clear, and goes to the 4p orbital. So now you have one, just see now what I'm showing on the slide please. 1, 2, 3 and 4. You have 4 orbitals which are vacant. So one belonging to the 3d, one of the 4s and 2 of the 4p. That's how DsP2 hybridized. Clear? So 4 ligands donating the 4 lone pairs. That's what see rightly seen here. Just see this part. So it's DsP2. That's one. And same way one of the platinum, this we had discussed in nature, PtCl4 2 minus, which is also platinum complex. And that also will be nothing but square planar geometry, DsP2 hybridized, where platinum at the center, 4 chlorine atoms at the 4 corners of the square plane. That's one. Clear everybody? So we say these D block elements can also form complexes, and the reason for this, one is the high charge by size ratio, small size is clear, higher the charge, and second, availability of vacant D orbitals. They can form complexes with ligands. Ferro and ferricyanide, the ligands are cyanide. Cuprammonium ion, ammonia is the ligand. And platinum tetrachloride, is this clear? If you remember PtCl, just see the formula here please. I'm giving the IUPAC name of all. People, you also give it with me. Let's try. Hexacyanoferrate, Roman number 3. Hexacyanoferrate, Roman number 3. Why to add 8? Because it's an anionic compound. FeCN6 4 minus. Hexacyanoferrate, Roman number 2. Hexacyanoferrate, Roman number 2. Cuprammonium ion. Tetraamine. Amine we write as AMMINE. Tetraamine copper, Roman number 2. Tetraamine copper, Roman number 2. Because it's cationic, so no 8. Alright, only it's anionic, then 8. Last one, PtCl4 2 minus over there. Tetrachlorido platinate, Roman number 2. Tetrachlorido platinate, Roman number 2 because it's -2, so PT has to be +2. Clear? So this is about the complexes. Then people's next point comes catalytic property. D block elements are the ones which are mainly used as catalyst. If you remember, in hydrogenation we had nickel used as a catalyst, nickel, platinum, palladium, all are used as catalyst. What's the logic of catalytic activity? One main important, its tendency to show multiple oxidation states because electrons are utilized from its valence as well as penultimate shell. And second, its tendency to form complexes. That's what you rightly see. So two parts I've already highlighted here, multiple oxidation states and its tendency to form complexes. That's why people on the surface, because it's adsorption basically. So these metals use as catalyst, so they have good catalytic activity on the surface. How? Just see this part. I'm just reading the slide, just see here. Catalyst at the solid surface involve the formation of bonds between the reactants and the molecules of the atoms on the surface of the catalyst by utilizing its 3d and 4s electrons for bonding. This is the bonds between the adsorbate and the adsorbent. Alright, chemical adsorption, so it's like covalent bonds. This has the effect of increasing the concentration of reactants at the catalyst surface and weakening the bonds of the reacting molecules. The activation energy is lowered. So people, the main feature of a catalyst, once it forms bonds between the adsorbate and the adsorbent, what is it doing? It is decreasing the activation energy. So if the activation energy is lowered, we all know, main function of a catalyst, it lowers the path. So if a new path comes of activation energy, reactants are quickly converted to products. So that's the point. So here people, what it says, look at that, iodide S2O8 with iodine and sulfate. So what is happening if you observe? Iodide is oxidized to iodine and S2O8 2- is reduced to sulfate. So how is it happening over here? First, ferric, this is in the presence on the arrow, I couldn't write, it's in the presence of iron 3 catalyst. Matlab ferric is the catalyst on this arrow. Okay, just see the slide. Iodide, please see on the slide please. Iodide is oxidized to iodine, S2O8 2- is converted to SO4 2-. On the arrow it's Fe3+. So what is happening first? Ferric reacts with iodide. Ferric, we know, will get reduced to ferrous and iodide will get oxidized to iodine. Done. Then again the same ferrous will further get oxidized to ferric and S2O8 will further get over there reduced to sulfate. So the catalyst took part in the reaction, formed an intermediate. When the reaction was over, the catalyst got regenerated. Clear? So the most important feature for catalytic activity, one, availability of electrons from its 4s and 3d, thereby showing multiple oxidation state, and over there its tendency to form complexes. Next people, next we have, this is the second last point, but some more time, 5-10 minutes, we are done. Tendency to form interstitial compounds. People, we have discussed this. What's interstitial compounds? Depending on the crystal structure, if we have very small atoms which go and occupy the in-between spaces, that's the voids, is this clear, of a particular element, then that's called the interstitial positions. If you remember, we have discussed in hydrogen interstitial hydrides, where the ratio where the hydrogen goes and occupies in between spaces, and because of that what happens, they are never in a whole number ratio. If you remember, interstitial hydrides do not hold good with respect to law of constant proportion. Matlab, we are not able to say that always they will combine in the fixed ratio. They may combine in any form depending upon the gaps available. Alright, so interstitial, occupying the in-between spaces, which increases the melting point of that particular element in which they will occupy. Secondly, now which atoms I am talking about? Atoms whose size is small, like hydrogen, carbon or nitrogen. Small size atoms occupying into the crystal structures of these D block elements, forming compounds where their melting point increases, they become more harder, their metallic conductivity will increase, and they become more stable. Alright, just see this slide please. Compounds in which small atoms like hydrogen, carbon or nitrogen are trapped within the crystal lattice, occupying the in-between spaces, that's the void. And look at this example, TiC, Mn4, Fe3H, VH.56, titanium hydride 1.7. So these are again same. Alright, They are either it's carbon or nitrogen or it's hydrogen which is going because the small size, but not in a fixed ratio. Alright, so occupying the in-between spaces, and because of that they have high the compounds which form these hydrides, these interstitial compounds of hydrides, or with carbon it forms carbides, or with nitrogen it forms nitrides. They have high melting points, they are more harder, they have good metallic conductivity, and they are also inert. Clear? That's one. And next we have people, this is the last part, that is formation of alloys. Alloys, what exactly is an alloy? People, with respect to solids, if I have to call, it's a solid solution, solid and solid, two solids combined together. Okay, so alloy is basically two metals combined, where we, if you remember, we discussed there can be two types of alloys: substitutional alloys and interstitial alloys. Substitutional, two atoms have the same size. Like for example, if I talk about brass is copper and zinc. Copper and zinc in the periodic table 2930 next to each other almost have the same size. So when I mix the two in a proportion of 1:1, what's going to happen? Few copper atoms will be replaced by zinc atoms, or few zinc will be replaced by copper atoms. So that's a substitutional solution, brass. We have bronze also, copper tin. It is clear? Where in this bronze, people over there, it's basically bronze contains copper, zinc and tin. So tin size is smaller, so tin goes in the in-between spaces. So that makes over there bronze more harder. If you remember statues are made up of bronze over there. So that's an example of interstitial solutions. So alloys is basically two metals combining. Is this clear? In a fixed proportion over there. Either they have the same size, or substitute, or that's substitutional, that having the same size, so one substitutes the other, or interstitial, where it goes and occupies the in-between spaces. Just see this part, what it says. Because of, look at that, because of similar radii and other characteristics of transition metals, alloys are formed by these metals. So they often have high melting points. Is this clear? And examples, like for example, steels and stainless steel. If you remember, we have discussed steel is mainly what? It's iron, but along with iron there is chromium, there is nickel also, and also there is some amount of carbon present over there which imparts hardness. Chromium to give it a shine, that's of chromium oxide. Okay, that's one. Now look at that. What is meant by disproportionation? We know this, people. Simultaneous oxidation and reduction of the same species. So look at that. Here it is Mn. Mn is in +6 state, so it's MnO4 2-. So the +6 will increase to +7, as well as it will decrease to +4 also. So that's what we have as disproportionation. Okay. And the last question, cupric ions is not stable in its aqueous solution. Now why cupric ions is not stable in its aqueous solution? What is the reason over there? Cupric ions, again here, cupric ions not stable because Cu+1 will have a configuration of 3D10. Now in 3D10, what will happen, people, over there? Cu2+1, it has got higher hydration enthalpy as compared to Cu+1. That is one. All right. And second part is also because of its second ionization enthalpy. Is this clear? So where, what do we say? The stability of cupric rather than cuprous is due to one, its hydration enthalpy, is this clear, then cuprous, which also compensates then the second ionization enthalpy of copper. All right. So cuprous less stable as compared to cupric. All right. Now with this, I think we are done with the periodic functions. Yes. Now with respect to this periodic functions over there, what do we call, people? With respect to this part, we will have over there, one second. Now, next class, we are done with the periodic functions. Next class, I'll be starting with respect to what we have as the next part of the chapter, that is about KMnO4 and potassium dichromate. Thank you.